My name is Courtney Smith. I am the lead staff here at the Air Resources Board, focused on sustainable communities research. Welcome to a research seminar entitled Quantifying the Comprehensive Greenhouse Gas Co-Benefits of Green Building. So before we get started, I wanted to give you guys a little bit of background about why we pursued this research. So the 2006 scoping plan and its update really lays out a comprehensive plan to address climate change that really cuts across sectors and includes strategies that seek to reduce greenhouse gas emissions that are associated with our built environment. So to support these strategies, ARB's Sustainable Communities Research Program was established back in 2011, essentially to provide the technical support to support both voluntary and mandatory strategies that aim to improve the sustainability of California's land use patterns, transportation systems, and also buildings. The land use and transportation related research that we conduct as part of this program assists with the successful implementation of Senate Bill 375, which essentially encourages smarter land use and transportation planning with the goal of reducing the distances that people have to travel to get to the places that they want to go. And our research on buildings really provides strong technical underpinnings that are needed for the Air Resources Board to not only propose improvements to the state's green building program, but also to advance voluntary green building programs. So in addition to the research that you'll learn about today, our other extramural research broadly focuses on quantifying the greenhouse gas impacts of climate strategies, as well as addressing some of the additional impacts, including exploring the ways to maximize, for instance, health co-benefits of our climate actions. So to learn more about our Sustainable Communities Research Program and the projects that we're pursuing, you can visit us on our website. The address is up there on the screen. Now, it's my pleasure to introduce today's speaker, Dr. William Eisenstein. Dr. Eisenstein is the Executive Director of the Center for Resource Efficient Communities at the University of California, Berkeley. The CREC is a research center focused on urban sustainability, climate change, water efficiency, energy efficiency, and land use. Dr. Eisenstein serves as the Urban Systems and Institutions Leader for the National Science Foundation's Engineering Research Center on reinventing the nation's urban water infrastructure. And he also serves on the California Air Resources Board's Research Screening Committee, reviewing diverse research pertaining to California's landmark greenhouse gas regulations and sustainable communities. Dr. Eisenstein has also served as a consultant to the State of California's Delta Vision process, the Delta Conservancy, the Delta Protection Commission, and the Central Valley Flood Protection Plan. He has also worked with Urban Ecology, Green Alliance, the Tri-Valley Business Council, and others on urban sustainability issues in the greater San Francisco Bay Area. So with that introduction, I will turn it over to Bill.
Thank you. Thanks for the introduction, Courtney, and I'd like to in turn acknowledge Courtney and also Dana Papke-Waters, who've been our contract managers for this project at ARB. They've done a terrific job guiding us through the process, and have had actually a lot of intellectual input into this project, so we are not the sole authors at Berkeley. Also with us is Kimberly Siegel, who you see her name's second only to mine in terms of the execution of this project. She worked with us for 1.5 years at Berkeley on this and is now with CB Richard Ellis, CBRE as it's now known. And so she has also played a major role in what you're going to see today. So what we're doing here today is reporting on the results of a project to estimate greenhouse gas emissions due to the water use, solid waste disposal, and transportation strategies that green buildings pursue. And in particular, commercial buildings throughout the state of California. So that's an important caveat to keep in mind from the beginning. We're focusing on commercial buildings only and certified green commercial buildings. But as Courtney sort of implied, there's a great deal of policy emphasis on green buildings as a GHG reduction strategy Much of that emphasis focuses, though, on the operational energy of the buildings and much less on these additional green building strategies, which are very important in their own right, but nobody previously has taken the effort to actually quantify what the greenhouse gas emission consequences of these strategies are. So both state and municipal greenhouse gas or climate action planning is focused heavily on green buildings as a strategy. At the state level, that's partly because buildings are such a big energy consumer and sort of stimulator of greenhouse gases that state policy, of course, has to address that. Municipal climate action planning also places a big emphasis on buildings because buildings are one of the things that are directly regulated by municipal governments through building codes and permits and so forth. So if you read a climate action plan from a city in California, you will almost certainly find a heavy emphasis on green buildings as part of how they're trying to meet whatever emissions target they've set for themselves. Again, that's a heavy focus on energy efficiency particularly. Sure. Okay.
Put it on the side, put it on the side here. No, like this right here.
Okay, hopefully that's better. It sounds a little louder even in here.
Yeah.
Good, sorry about that. But again, no full accounting of the benefits of these additional green building strategies. So our goals here were to obviously achieve a more complete assessment of the potential GHG benefits of green buildings, also to facilitate progress toward GHG goals by allowing fuller accounting of green building benefits, not just focusing on operational energy, potentially stimulating voluntary actions to reduce emissions by documenting the role of green buildings, and also importantly to inform future building standards setting. So many of you may know that the state of California, not the Air Resources Board, but other portions of the state, produce building energy efficiency standards, Title 24, Part 6, the now Cal Green Code. These are important in establishing baselines for municipalities to set in their building energy standards. So to the extent we can inform those processes, that's also very valuable. So just to lead with some of our big findings, and then the rest of the talk is going to sort of be substantiating and describing how we came to these conclusions. We found that green office buildings, compared to conventional construction, are producing about 50% less GHGs due to water consumption. And for those on the web who may not be used to the lingo, GHGs is short for greenhouse gases. I will use that acronym numerous times throughout the talk. 48% less GHGs due to solid waste, and about 5% less GHGs due to transportation. If the entire California office building stock achieved performance typical of these certified green buildings that we looked at, the state would be saving about 0.831 million metric tons of CO2 equivalent, or 831 million metric tons, however you want, 831 metric tons, however you want to look at it, of CO2 equivalent per year. So again, we'll go into detail about how this conclusion was achieved. Basically, the study is organized around a set of analytical comparisons, and apologies if this is a little bit small for you, but it's an important table. In the left column, you see the names of 3 different values that we measured or estimated as part of this study. Baseline values are performance of typical non-green office buildings in California. So just something that's constructed out in the marketplace, not striving for a green rating, but is state of the art, meets state standards for construction, but is otherwise typical. The predicted value, the second one in the middle, is performance expected of green office buildings at the time of certification. And I'll talk a little bit more about why that's significant, but we are studying a set of buildings in our work here that were certified at a particular time. They were certified green under the LEED system, which I'll talk about in a moment. At that point in time, there were certain expectations that were embodied in state policy for how a green building should be performing. So that we're calling a predicted value for what this building would, how it would be performing. And then finally on the bottom, the measured value is the actual performance of the green office building. So essentially we're making two comparisons. We're asking, what's the difference between the measured value and the baseline value? In other words, what's the difference between the actual performance of a certified green building and typical office construction? That's one question. Another question is, what's the comparison, what's the difference between the measured value and the predicted value? Is the certified green building actually performing the same way that the prediction would have anticipated? That's important because, of course, it's predictions that we're basically relying on in GHG reduction efforts. We're trying to set policies that we think are going to have certain impacts in terms of reducing greenhouse gases, so we want to get a handle on how good our prediction methods are, essentially. The whole section to the right there, major data sources, is, again, something I'm going to go through as we talk here, but these are some of the sources that we relied on for data on each of these sort of cells in the matrix. So the baseline values for water came from a certain source. The baseline values for waste came from a certain source, et cetera. So these are just documented here. I do want to focus you, though, on the bottom line, where you'll notice that all the measured values came from the same source, which is performance data from certified green buildings that were certified under the LEED-EBOM system, which is LEED Existing Buildings Operations and Maintenance. For anyone who's not familiar, LEED is a rating system created by the U.S. Green Building Council. It's a voluntary system. Buildings, when they're constructed, can strive to achieve a green rating under LEED. These are existing buildings who are undergoing renovation and management changes, and they can also seek to achieve a rating, a positive rating under LEED-EBOM to certify themselves as green. So LEED as a source of operational data for these buildings has important strengths and weaknesses that need to be talked about at the outset. Because they have important implications for the findings here. So the strength is that this particular form of LEED, the Existing Buildings Operation Maintenance data set, provides operational data. That's one of the things the buildings have to do to get the rating, is to measure their own performance in many areas, including the three we're dealing with. Other LEED systems, that's not true, because other LEED systems, the certification occurs at the moment of construction. So the building hasn't operated yet, so there's no data to report. The weakness is that there is, in LEED-EBOM, very little information on the strategies or what the specific actions that the building took to reach these performance levels. They measure performance level, they get a certain amount of credit for that. They also may be striving to improve performance to a certain threshold that's identified in the rating system. So for example, in water, as I'll point out in a minute, they can seek to reduce their water use by 30%. They get extra points for that. But it doesn't give us any information on what they did to reduce the water use by 30%, only that they did it, potentially. We are also focused, I mentioned earlier, we're focused on commercial buildings. We, because of the nature of this data set, essentially had to operationalize that as office buildings only. So we focused on office buildings and excluded other kinds of commercial buildings. They vary enormously in their performance characteristics. Both a warehouse and a restaurant are commercial buildings. So you can see that there'd be an enormous difference in the transportation intensity, the amount of water used within that structure, that they're really just so dissimilar that generalizations are almost impossible. Office buildings, by comparison, are relatively homogeneous. There's many more of them than there are the other kinds of commercial buildings in the data set, so we focused on that. And we worked with buildings that were certified under the LEED-EBOM versions of 2008 and 2009. So the buildings that were certified under the systems generally were achieving the certification in the handful of years following that, typically between 2010 and 2012, because they were working under a system that was invented and published in 2008 or 9. So mostly these were 2010 to 2012 certification buildings. But again, existing buildings that had been standing for longer than that. I mentioned this, but LEED is a menu, not a recipe. You have, if you're seeking to get certified with your building, you can choose many different ways of doing that. There's different points available. Your building, there's a few prerequisites, but otherwise you can choose whatever you want to do. It's not a prescriptive set of things that you have to do. in the cases that we're looking at, buildings could get credit simply for measuring the usage of water, waste, and transportation, irrespective of whether they're doing anything to reduce those things. But then there are additional credits available for achieving specified performance levels, and I'll talk about that in each individual case. Again, minimal information on the strategies used to achieve those performance levels. So, excuse me, for those of you who may be well versed in LEED-EBOM, we wanted to mention the credits that we worked with. So these are essentially the measured data, the measured values that were the basis of the study. So the first set there is the water efficiency credits. The prerequisite is to achieve either 120% or 160% water usage compared to the 2006 International Plumbing Code. Again, that sounds unambitious, but again, these are existing buildings that had been built perhaps long prior to that. So bringing it up to roughly a 2006 plumbing code standard actually in many cases is a substantial improvement. Then water credit 1.1 is simply to meter the whole building's water use and report it. They got a point simply for measuring it. 1.2 is to report on any sub-metered usage. So they could sub-meter any portion of the water usage, maybe the irrigation usage, maybe the indoor usage, maybe the cooling tower usage. They didn't have to do all of them. They could just perhaps do one and get the credit for that if they reported it. Then water credit 2 is the one that offers points for achieving up to a 30% reduction in indoor water use. With the materials and resources credits, the MR, which is solid waste in our language, the prerequisite is simply to have a solid waste management plan. The credit number 6 is to report on a waste audit that the building does over a period of time of its choosing. And that can be reported either volumetrically or by weight, and it distinguishes between the amount of waste diverted, i.e. sent to recycling or composting facilities, versus the amount disposed, i.e. sent to landfills. And then credit 7 is to divert at least 50%. You get a point for diverting at least 50% of what are called the ongoing consumables. So that's the materials that we use in everyday life in an office building, plastic bottles, water, what have you, but it's not things like construction waste or durable goods like chairs, computers, and so forth. And then for transportation, we're relying on only one credit, which is Sustainable Sites Credit 4, which offers points for reducing the average vehicle ridership, or AVR, by up to 75%. The average vehicle ridership is essentially the quotient, the ratio of the number of people working in the building divided by the number of cars it took to get them there that day. So the more people travel by some mode other than the automobile, walking, bus, or carpooling, the higher the ratio will be. If everybody drove their own car to work, it would be a 1-to-1. The AVR would be 1.0. So the higher, the better, the more sustainable in that case. So this is then the data that we have and worked with. So for water, we have total usage in the building. We have a very fragmentary set of sub-metered data. Not all buildings sought that credit. Those that usually didn't sub-meter all the systems. They just chose one or two. And then we've got a certain subset of buildings seeking the indoor efficiency credit, the 30% reduction in water usage. For waste, we have a diversion percentage as the data point that we are able to work with. Because the time span of the waste audits was all over the map, and the timing also of them, what point in the week or what point in the year that was done. We couldn't sort of compare directly on the quantities of waste that were disposed or diverted. We were only able to look at the percentage diverted, i.e. recycled or composted. And then also we have this data on a smaller set of buildings seeking the 50% goal. And for transportation, we have average vehicle ridership data. Some of these things vary regionally around the state of California, and so we had to account for that also. So we know that there's regional variations, for example, in irrigation demand. It's hotter, inland, and there's more evaporation inland than there is on the coast. The energy intensity of water varies around the state. It takes a lot more energy to deliver water to Southern California than it does to Sacramento, where you're basically pumping out of the Sacramento River and there's almost nothing required to deliver it to buildings in the city. And then regional transportation infrastructure also varies quite a bit. The Bay Area has a lot of rail systems and bus systems. Sacramento has a good share as well. San Diego, not so much. So there's a lot of variation that has to be accounted for. So we performed all the calculations you're going to see for 5 regions of the state. Basically, the big 4 metro areas, Bay Area, Los Angeles, San Diego, and Sacramento, and then a 5th region, which was called Rest of California and encompassed everything else. So this is the size of our data set then, broken down by the regions, the 5 regions. So for the transportation data, we had 196 buildings after we sort of cleaned the data set and took out the buildings that, for whatever reason, the record didn't make sense. For water, about 191, and for waste, 233. So that's sort of all the big picture. And now what I want to do is talk through, and I hope to not go into numbing detail about these things, but to describe for you so that you can understand how we derived baseline, predicted, and to some extent measured values for each of these resource areas. And then also importantly, how we looked and thought about the greenhouse gas intensity of the usage, which is sort of a 4th thing that has to be added on, or it's a factor that has to be applied to all of these things to get a GHG footprint for these usage levels. So we'll start with water. And for baseline water use, there's essentially 2 good studies out in the literature that we were able to uncover, one of which had 2 different approaches to the question. And you can see on the slide here, I'll try to get my pointer up, that these are expressed in gallons per square foot per year of usage in the building. You can see in the bottom here how drastically these vary. From one study from the American Water Works Association finding over 500 gallons per square foot per year of usage in the left column, over to the rightmost column, which is one of the 2 approaches taken by the Pacific Institute, which is finding only 108 gallons per square foot per year. Most of the difference, as you'll maybe have noticed already, is in the irrigation values. And this AWWA study in particular was focused on buildings that were concentrated in Southern California and even actually in the relatively inland parts of Southern California, like San Bernardino County, for example, where irrigation demand is much higher than it is in coastal places. We used the most conservative of these 3 baselines, i.e. the one on the right, because we knew that we would be comparing the performance of green buildings to these baselines, and we wanted to be as conservative as possible about the benefits that we were estimating for the green buildings. So we chose the 108.1 gallons per square foot per year. Predicted water use then, as I mentioned, the predicted value is what a green building at the time of certification was sort of expected to achieve. And so one thing that's useful here is that CalGreen, the green buildings standard for the state of California, which is now mandatory, but it was not mandatory when these buildings were being certified under LEED-EBOM. It had been published, but it was not yet a mandatory building standard for commercial buildings in the state. So we used the expectations essentially that were codified in CalGreen to formulate the predicted values for water. So that essentially is a process for indoor usage of identifying the sort of fixture and fitting standards in the plumbing code, the rates of usage associated with that, the population in the building, to achieve an overall estimate of what the indoor water usage from a certain size of building will be as a result of those plumbing standards. So that's for indoor use. Then there's also irrigation usage. Again, varies considerably around the state. CalGreen refers applicants to the Department of Water Resources Water Budget Workbook. So we used the same source then to estimate for the regions. We chose the biggest city in each of the regions to what the irrigation demand would be. And then we expressed that per building square foot as opposed to per square foot of land that's being irrigated. That's an important distinction that changes the numbers quite a bit. For measured water use then, again, I mentioned we had this sub-metered data, and the sub-metered data, though, is fragmentary. It would have been very handy if all the buildings that sub-metered had done all of the possible, I think there were 5 possible sub-metering configurations. So if they had done indoor irrigation, cooling tower, process water, et cetera, and had a complete set, it would have provided a lot of mathematical simplicity for us. But we had this fragmentary set. So instead, what we did to derive, we had the measured water usage for the building, but we wanted to distinguish between indoor irrigation and cooling tower usage. Because as you saw, the irrigation in particular is a big driver of overall usage. So we calculated the average total building usage for all buildings. We then calculated average irrigation usage for the buildings that were sub-metering irrigation, and the average cooling tower usage for buildings that were sub-metering cooling tower usage. And then we sort of imputed the average indoor usage by subtracting the irrigation average and the cooling tower average from the total building average. And then those results were broken down by region. And then finally, we've got the GHG intensity of water. The greenhouse gas intensity of water, again, varies throughout the state. For each of the regions, you see them listed on the left there. We had to assume something about the origin of the water. Every region gets water from many different locations. The energy intensity of those supplies differs considerably. And so we took what's known as a marginal water approach, assuming that as water is saved, the water utility will sort of cut from certain sources first. It won't be a portfolio-wide average. It will be a certain source that's either the most difficult to get, the most unreliable, the most expensive, what have you. That's the one they'll sort of give up on first. That's a standard approach in sort of water energy studies. And we, in general, assumed the same marginal sources as other studies in this vein have done. We also assumed that for those sources that we would take a marginal energy approach, so that as energy is saved as you give up water imports, you also are cutting, the energy utility is cutting from its most unreliable or most GHG intense source first. And so we then used an estimate for the marginal GHG intensity of energy throughout the state. The only exception to that is in Sacramento. You may notice in the middle of that long column where the GHG intensities are. I'll try to make my pointer come up. That the Sacramento value for the GHG intensity of energy differs from the others. Doesn't seem to be responding, but that's because the average the average GHG intensity of the entire energy portfolio in Sacramento is actually lower than the marginal value for the rest of the state. Basically very clean energy in Sacramento compared to others. So these GHG intensities of water then were applied to calculations of the GHG footprints of baseline predicted and measured values of water. We'll get to the results of everything in a couple minutes. The baseline for solid waste, much simpler. There's basically only one good resource for uncovering some of this information, which is studies done by CalRecycle, essentially statewide waste audits. The waste generated by large office buildings is conveniently estimated at 1,998 pounds per 1,000 square feet, almost exactly 1 ton per 1,000 square feet. But the best baseline information on the diversion rates was found in this 2006 CalRecycle study, which found that among office buildings, only 7% of the ongoing consumables were being diverted at the time of this study. Now it says 47%, the largest piece of the pie there, 47% could be easily diverted, i.e. it's probably office paper and other things that aren't being recycled reliably. But on the basis of this one study, which really was the only good one, we established the baseline diversion rate at 7%. At the same time, Assembly Bill 341 was being passed and establishing a 50% diversion rate goal for jurisdictions, not for individual buildings, but for jurisdictions. And we took the liberty of assuming that that represented a reasonable aspirational goal for green building at the time. Again, at the time of the certification, now that would be probably seen as unambitious because the state has new goals on the books. But in 2010, 2011, that was the goal. And folks at Cal Recycle and ARB agreed with that. So our predicted solid waste diversion rate was 50%. For measured solid waste, again, we had these waste audit data. And these are organized, each row in here is a building. And they're stacked by their diversion rate, the lowest diversion rate at the top and the highest at the bottom. Disposal and diversion rates are complements of each other, so they sum to 100%. So that's why the graph takes that nice sort of flowing shape to it, because the total width of every bar is the same. And the fact that you can't read the details on this is actually fine, because the squint test tells you what you need to know, basically, which is that of the waste being disposed, much of it is that sort of pale green color, which represents wet waste, food and so forth being disposed. And on the right, what's being diverted, i.e. recycled, is mostly the red, which is mixed paper. So in an office building, that's not terribly surprising. But at any rate, we have this diversion percentage data. And again, we'll talk about that more in a couple minutes. Solid waste has a greenhouse gas intensity. We used formulas from the landfill emissions tool that is in use by ARB and other state agencies. Based on the graph you just saw, we assumed that about 70% of the landfilled waste was wet waste, and about 30% of the landfilled waste was paper. And we assumed that the landfills have gas collection systems, i.e. methane systems. Not all of them actually do. But we, again, wanted to be conservative in terms of the GHG impacts we were attributing, and went ahead and assumed about 2/3 of the landfills in the state have them. The rest there's state incentives and policies to put gas collection systems on the rest of them. Essentially, it's methane coming out of these landfills, primarily from degradable carbon in these waste products. And then we were able to then convert the methane emissions into CO2 equivalents to make them comparable to the findings in the other areas. And then for transportation, and we'll get to the results quickly here, we have a process that actually we invented whole cloth, because most transportation studies are not done, they do not focus on average vehicle ridership. Most of them focus on vehicle miles traveled. Which actually is the more sort of directly relevant measure for greenhouse gas impacts, because greenhouse gas emissions are basically directly proportional to how much petroleum is combusted or electricity is burned to move a vehicle. But the average vehicle ridership data is what we had from the LEED-EBOM set, and so we had to think of a way to create a baseline for AVR for a region and then also a predicted value. So for the baseline, we turned to the American Community Survey data, which is basically an operation of the U.S. Census that collects data on commuting patterns annually, and then it aggregates them in either 1 year, 3 year, or 5 year chunks. So we looked at the span from 2008 to 2012, and essentially the regional baseline AVR then for each of the regions is, and this is basically simple addition and then division of the data, the number of commuters over the number of vehicles, adjusting for the fact that there's carpooling. That's essentially what that formula says. So that led us to discover what I think is the first time this has ever been calculated, the baseline average vehicle ridership for these major California regions. Unsurprisingly, the Bay Area is a bit ahead of the others. You know, the BART system's 40 years old. There's a lot greater density in the office core, at least in San Francisco, than in many other parts of the state. There's Muni, there's Caltrain, there's bus systems. There's a lot more pre-existing transit infrastructure than in the other regions, although, of course, LA is catching up as quickly as it can in terms of that investment. So essentially, our logic here is that a typical building, again, remembering that the baseline value is sort of the typical office construction. we're sort of taking the assumption that they're sort of located in a typical location, an average location within this region, so that their AVR, the AVR of the building would be reflective exactly of this regional baseline, this regional average ridership. Then producing a predicted value from that also is really a function primarily of location. And there is a formula, fortunately, in the guidance from CAPCOA. I don't know how many of you have encountered CAPCOA. It's the California Air Pollution Control Officers Association. They have a manual of techniques for estimating greenhouse gas emissions impacts of various strategies, green building strategies, and other things. And they present in there a strategy for calculating the mode share of transit based on, as a function of distance of the destination to transit. So how far the building is from, in this case, rail stops, is expected to increase the rail ridership, the mode share, i.e. the percentage of people, the proportion of people in that building going to work by rail by a certain amount. And that's what that formula basically expresses. So we then use that to adjust the baseline regional AVRs according to the location of each building by increasing the number of rail trips relative to the regional baseline as called for by this formula based on location of the building. I should point out that's also a conservative approach. It doesn't include things like bus, things like walking or bicycling, any other mode. The formula is based exclusively on rail. So we're going to end up with a predicted value for transportation AVR, which is lower than we might otherwise expect. In other words, you could think of, if you had predicted values, formulas that were predicting all these other non-automobile modes, you'd get a higher predicted AVR than what we're ending up with here. And then for the measured data, again from the LEED-EBOM system, we encountered the challenge that we didn't actually have the precise AVR for each building. The data was binned. So they would seek to achieve a certain reduction in their, or certain improvement in their AVR, the so-called demonstrated percentage reduction in conventional commuting trips. So the column on the left, they can get points. They'd be rewarded for anything ranging from a 10% to a 75% reduction in conventional commuting trips. So you can think of that as an AVR anywhere between 1.1 and 1.75. But we don't know within each bin exactly what the AVR of each building was. So we assumed that the measured AVR, in fact, was 25% above the lower threshold of the bin in order to not be overly aggressive in terms of how these buildings are performing, to try to be conservative in our estimations. The GHG intensity of transportation, and so we'll get to results right after this, is also an important factor. In fact, it's probably the most important factor of all of these we've discussed. And so in order to attribute this, we took a weighted average of the greenhouse gas intensities of each of the modes in use in that region, proportional to the regional usage rate. We assumed that the building occupancy rates were the same as what is considered standard in the plumbing code, so that's 5 occupants per 1,000 square feet. And we assumed the average commute distance of 24 miles per person per day, which is actually a surprisingly constant value in studies that actually range through all 4 of the big metros in California. LA and the Bay Area, surprisingly, are not that different in their average commute distance. So all of this is essentially needed in order to convert an average vehicle ridership into something which is, has a GHG footprint and is proportional to the size of the building and can be expressed, therefore, on a per square foot basis to be commensurate with the other resource areas. So results here then, and I actually, for those in the room, this handout was on the back table because and I wanted to provide this because it gives you the actual data as opposed to the bars on the chart here. But it's the same substance, so for those on the web, you can read off the y-axis, hopefully, and get a sense of how high these bars are and visually you can sort of sense what the percentage differences are. But I just thought this would be more informative for those in the room, and these numbers get way too small to read on a screen, so that's why it's in a handout. So for water results, what we're seeing here is the results from all the buildings broken up by the usage type. So the different colored bars are the different usage types. The purple is the total building water usage, so it's the sum of the other 3 bars. The blue is indoor water usage, the red is irrigation usage, and the green is cooling tower usage. And you do see on the left with the water usage results, again, all expressed in gallons per square foot per year, so everything is normalized and comparable. A substantial improvement in between both the baseline on the left and the measured, which is the third set. And you also see that the measured values are considerably better than the predicted values. And so you can find that these were actually stapled backwards. So the staple, you should actually look at table 13 first if you're curious about this. I don't know why those are backwards. But you find, for example, that the total building usage statewide, comparing baseline to measured values, is a 50% reduction. And from predicted to measured values is a 13% reduction. So in other words, the green buildings in terms of water usage were performing even better than prediction. And I should have made clear that actually those results pertain to the GHG emissions. The usage, actually, the improvements are even bigger, but GHG emissions are those numbers I just quoted. It's important to remember that GHG emissions do not necessarily track directly, linearly with usage rates, because again, the GHG intensity of water is not the same around the state, and it's also not the same among these usage categories. Indoor water used indoors is much of it is heated, so that's a big energy input, and also it goes to sewer systems, wastewater treatment plants. There's a big energy input in treating wastewater. Irrigation water is neither heated nor is it treated in a wastewater treatment plant generally. There's a couple of exceptions around the state. But that's so that water has much less GHG intensity associated with it. So indoor usage is the place to save if you are seeking to reduce GHG emissions. Waste results, and these are given in greater detail. Oh, sorry, I should have mentioned one other thing. This table also includes, or this bar chart also includes the so-called high performance buildings. So these are the buildings that were seeking the credit, getting the credit for reducing their water usage by 30% below their own previously measured baseline. And an important realization here, an important conclusion of the study, is that those buildings actually did even better than that. Their reduction compared to the buildings that were LEED certified but not seeking that credit was actually significantly bigger than 30%. So that incentive appeared to be operating pretty effectively. With waste diversion rates, the data is a lot less complex because we're basically comparing 7% to 50% and then what our measured value is. So our measured diversion rates on the left, hopefully I can, yeah, here we go. We're just above, we're basically at 52%. This is showing Bay Area and LA data along with the blue, which is the total statewide. So we're at about 52% diversion, slightly above prediction, which was 50%, hugely above baseline, which was 7%. And so the GHG emissions, which in this case are inversely related to the diversion rate because the diversion is more cycling, you're seeing very large drops in the GHG emissions, both predicted and measured relative to baseline. Again, we have this set of buildings that were getting the credit for doing 50% waste usage, waste reduction relative to their own baseline. And again, those buildings overperformed that target. So again, the incentive appeared to be operating effectively. Transportation results, these are the average vehicle riderships. And there's a little bit of a different story here, where even though we used that relatively conservative prediction method that excluded buses and walking and everything other than rail, Nonetheless, our green buildings are not meeting, in this data set, we're not meeting the levels of AVR predicted for them by that formula. So the measured values are an improvement over the baseline of about 5% in terms of GHG emissions, but they were falling short of the prediction by about 6%. I'll talk in a minute about the significance of this, but you can see that data on the bar chart, and then that is actually table 17 in the handout. So this I did put up, and I hope this is sufficiently legible for people on the web. You have it in your handout as table 18. This is the summary of the GHG emissions rates from these 3 resource areas for certified green office buildings, expressed as a GHG intensity for the building. So this is GHG emissions, so this is metric tons of CO2 equivalent per 1,000 square feet per year. And in the left, for example, the baseline values, we've got water, waste, transportation, and then for comparison, I also included operational energy in this chart. You can see that the transportation intensity of the buildings is enormously higher. The GHG intensity of the transportation is enormously higher than that of the water and waste. And significantly, and to me somewhat surprisingly, it's actually also significantly higher than the operational energy, about 2.5 times as high. So all the energy used to heat and cool the building, to turn on the lights, to run the computers, et cetera, is only about 40% as much in terms of its GHG impact, I should say. It's only 40% as much as the transportation that is used to get the people to the office building each day. And so this is, I think, an important finding, but each of these, again, hugely larger than the water and waste. So in terms of this study, transportation is where the action is for baseline predicted and measured, that has important consequences for policy and for recommendations. So using that GHG intensity data, we then produced table 19, also in your handout, which is looking at what we'd be saving as a state if the typical office building achieved the same performance as the certified green office buildings, or if the entire California office building stock were upgraded to the point where it's performing comparably to these certified green buildings. And so the average office building is a little under 13,000 square feet. Achieving these emissions levels or these GHG intensities, again, most of the savings, this is metric tons of CO2e per year. You're in the 175 range in terms of a baseline, and down to about 170 metric tons per year for an average office building. There's about 1.14 billion square feet of office space in California. And so if that entire office stock were achieving these emissions levels, we'd be saving, as a state, this much, about 831,000 metric tons, or 0.831 million metric tons. If they were all able to achieve the levels characteristic of the higher performing buildings, the ones doing the 30% water and the 50% waste reduction, we'd be doing marginally better at about 876 or 877,000 metric tons saved. Again, that's another way of saying transportation's where the action is. You can do really well on water and waste, that's good, but for GHGs, transportation is what you need to do. So some major conclusions. I just said the first one, water and waste performance are significantly better for certified green buildings. In both cases, about a 50% usage drop, so that's really non-trivial. That's an important improvement. The extra performance incentives are prompting even greater efficiency performance than the LEED-EBOM system itself is rewarding. I didn't go into a huge amount of detail on this, but performance and prediction were diverging most starkly for the irrigation usage as well as for the transportation. So as I said, the buildings did not achieve the level of transportation performance predicted for them. It is important to realize that that could be a product of the shortcomings of the prediction method, as opposed to the shortcomings of the buildings. You could look at it either way. In fact, we do need to improve our prediction methods pretty significantly. I described what we did here, but there's probably all of you have realized there's a number of ways these could all be improved. Transportation issues in particular, as I said, the prediction method is conservative. It is important to realize that buildings certified in other LEED systems may be performing better on transportation than these existing buildings. Other LEED systems are giving points for specific strategies that a green building can take. So you might provide preferential parking for electric vehicles. You might have a van pool program. You might have a commuter savings program. Any of those things, those all get credited under other LEED systems. This LEED system didn't have any of that. It only asked people to measure their performance and to, if possible, achieve a reduction in it. So I think it's reasonable to think that newer buildings that are instituting some of those strategies might be performing better on transportation. And then also you'll recall that we assumed the 24 miles per person per day as the commute distance round trip. But trends in commuting distance are hugely important to shaping transportation GHGs. The greenhouse gases are proportional to the distance traveled. And so if you're wrong by 10% on the distance traveled, you're wrong by 10% on the GHG emission estimate. And 10% of this is a big error. I mean, it dwarfs the water and waste all by itself. And so understanding trends in commuting patterns is very important, and there's been other research done on that. I am sensitive to time, and I'll tie up with a couple of extra slides here. The LEED-EBOM buildings are existing buildings, and so these findings might have the most pertinence to retrofit efforts. Again, we have 1.14 billion square feet of office space. It's not going anywhere anytime soon. And so as we focus on greenhouse gas emissions in the future and reducing those by 80% by 2050, which is the state goal, we have a lot of work to do on retrofitting that existing building stock. New construction with existing standards and now the CalGreen system should be able to do better, as well as the continual upgrades in Title 24 Part 6. CalGreen has taken effect now, and it has prescriptive but not yet any mandatory performance thresholds for the 3 resource areas we're talking about here. So there is room to upgrade CalGreen in future revisions, future updates of it, to put in some tougher requirements basically for these 3 resource areas. ARB in the 2006 scoping plan established a goal of achieving 7.5 MMT of CO2e per year emission reduction from green commercial buildings, not just office buildings. So the results I was reporting were, again, just office buildings. That's not including restaurants, hotels, warehouses, educational institutions, a large range of other commercial buildings that are included in that stock. That goal also includes operational energy, but it doesn't include transportation. So the results of this study are not really directly comparable with it, but there is a lengthy discussion in the report, if you're interested, arguing that these results actually are consistent with ARB's overall goals, particularly in the water arena, which is the one area that overlaps really directly. Another thing that's important to remember is that the GHG intensity of water, as well as operational intensity of buildings, is actually going to be dropping over time because the electricity system is getting cleaner. So we're getting more renewables supplying our electricity, less coal and natural gas, although natural gas is increasing in the short term, but it hopefully in the long term will be decreasing. So all of the GHG footprints that are associated with those energy inputs are going to be dropping. So in that sense, end-use efficiency will be of declining importance, not that it's unimportant, but it will be of declining importance relative to other things over time. So we're urging, as a result of this, that the state address transportation emissions through CalGreen or other building codes if possible. It's just too big to ignore. If it's 2.5 times the size of operational energy, then it needs to be addressed in terms of thinking about the impacts of buildings. We need to improve baseline and prediction calculation methods, again, especially for transportation, because small errors can lead to big errors. And then CalGreen should also be strengthening its plumbing standards and requiring composting facilities in buildings, because as you might recall, there was a big fraction of those bars for the disposed waste was wet waste. i.e. compostable waste. So facilities for that is an important thing for reducing further the solid waste leaving buildings. It's important to encourage all buildings to make performance data public. We only could do this study on green buildings because green buildings take it upon themselves to publicize their data. And in fact, the U.S. Green Building Council, it doesn't require it, but it facilitates the dissemination of operational data from buildings. And so there is nothing comparable for typical unrated, uncertified buildings. We would learn a lot if we had that data. We can include questions on water, waste, and transportation in the 2 major building energy surveys that are done, the California End Use Survey, which is a state survey, and then the CBEX, which is a federally sponsored survey of commercial buildings. And we also need to expand emphasis on existing buildings in climate planning efforts. There's a lot of policy around new construction. That's what Title 24 Part 6 applies to, and Cal Green largely applies to. And there are retrofit standards in each of those codes, but given the size of the existing building stock and its relative inefficiency, there needs to be a lot more effort put into that. So, time for questions. And I realize I also didn't put my center's web address on here. If anybody's curious about that, it's crec.berkeley.edu.
Thank you.
So. Peter, are you the MC? Okay.
Question?
So it wasn't clear if the buildings that you used for the predicted values went through the rating system and then were subject to EBOM, or if it was a different set of buildings. Is that clear?
The predicted values were not based on real buildings. They're imaginary buildings.
So they were just basically using the thresholds of the rating system to come up with those values, and then I'm just trying to understand the connection between the predicted values and the measured values. So it was the same set of buildings that you ran through one and then the other, or was that just based on the rating system?
Well, the predicted values are, as I mentioned, sort of derived from these state standards. So there wasn't a set of buildings, there weren't any formulas or any particular specific set of buildings that generated those. It was based on a policy expression by the state of California at that time of what a green building should be achieving. So there were plumbing standards and irrigation standards that we utilized, and then there was this waste diversion standard, which was basically 50%. So they weren't real buildings.
So then what about the second part? As far as, was that just separate, just looking at EBOM, what are the policy effects of EBOM, not on a green building, but just on a building that's been subject to EBOM?
If I'm understanding the question correctly, I mean, the EBOM, we basically just used EBOM as a reservoir of operational data. And because it doesn't have information on the strategies that the buildings took in order to achieve their performance levels, we couldn't make any conclusions about which strategies were achieving which outcomes. And so basically it's saying, okay, if certified green buildings under EBOM had these performance characteristics, the state was expecting green buildings to perform the following way based on these policy and code sources that we have. How did those compare? Is that answering? Sure. Yeah. This is Kimberly Siegel, who...
Hi, I'm Kimberly Siegel.
She assisted us with the study.
Yeah, so I also worked on the study with Bill. And so if I'm understanding your question correctly, we got access, we got actual submittal data that was given to the USGBC from, I don't know if that table is in here, the one that lists how many buildings we had per credit. So we were able to actually see what was submitted. So while Bill is speaking to the performance criteria of those credits, we were able to see the actual data they submitted. It might not actually reflect, okay, they achieved a performance greater than 50% or 75%, but we were able to see some of those details of, okay, for instance, the transportation credits, they achieved at a minimum 10% greater AVR than...
So those were real buildings?
Those were real
Those were
buildings.
real.
In those instances, those are actual buildings in California that have submitted under LEED for existing building, either under 2008 or 2009 rating systems. Yeah.
Yeah. And that's why I said what I did at the end about when we're comparing predicted and measured values, we can say, okay, the buildings are falling short of the prediction, but it also might be that the prediction method isn't accurate enough. I mean, they were, there's two ways to improve that.
So it looks like we have a long way to go in the AVR category for transportation. Can you take a guess what your results would have looked like if you would have included all the alternate transportation modes?
I can almost guarantee they would look worse for the green buildings because, again, the prediction method was conservative because it only included rail, and yet the green buildings didn't yet achieve even that conservative prediction. So the more extra modes we'd include, and bus and bicycle are probably the two that are important. Walking is still, unfortunately, a very small sliver because our land uses are too spread out. It would make them look worse. But rail is the big alternative mode in the sense that, in the Bay Area, it's about 13% of commuters using rail, BART, Caltrain, and so forth. Buses are much less than that, 3 or 4%. Bicycling is about the same. But yes, we do have, it's not only the most important area in the sense of having the most GHG intensity, but it's also the most important area in the sense that we're not making nearly as much progress as we are on the other ones.
This is just a little logistical question, but some of the slides early on were difficult to read on here. Is there any way to have access to your slide presentation?
Sure.
Okay, so
I'm sure it's either through ARB or us. I'm sure it's doable.
I did have a question on the waste. You have the assumption of 70% wet waste. What's that based on, since the 2006 recycle study estimates about 25% food waste is disposed?
That was based on the character of this data, essentially. So everything left of the midline there is what's going to landfills. The very faded out, it's probably even worse on the screen, but the majority of those bars, that's actually not a null value, that's a color. It's a very light green color, which represents the wet waste. So you can see how much of that moving up the chain there is wet waste.
And those
Kim,
are the 233 buildings.
yeah, Kimmy's pointing out these are the actual 233
Yeah, these are the
LEED-EBOM buildings.
Yep, precisely from the LEED submittals we collected.
Yeah. Your question's relevant in the sense that that's a fairly, wet waste is a fairly GHG intense form of waste because it has a lot of degradable carbon, so there's a lot of methane being produced. So it's another area where variations in the input, this isn't so much an assumption, but we're inputting based on this data. But if it were different, the methane produced would be lower and the CO2 equivalent would be lower.
Okay, well, with that, thank you so much, Bill, for coming down and presenting this research. For folks in the room and also audience joining us on the webinar, his presentation is available on our research seminar website. And in addition, we will go ahead and post the handout that he brought for folks in the room today, so that way everyone has access to it. Great, thank you.
Thank you.